Welcome everyone again to the last session of today. This session devoted to deep learning fundamentals and applications. So my name is Joan Serra. I'm a researcher at Telefónica Research, and I will be the chair of this session, together with Petya Radeva from UB around here, Jordi Torres from Barcelona Supercomputing Center, which I didn't see him, maybe he's not here now, and Joan Brunner from NYU, who couldn't come today. So the first keynote speaker is Alexandros Karatzoglou. He is the scientific director of Telefónica Research. And he was well known before, for me at least, for his work on supervector machines and kernel machines, and also for his learning to rank methods applied to recommender systems. So actually, if you allow me a bit of a personal note, that's what I prepared when I went to the interview at Telefónica. But then what I found, that was in 2014, by the way, but what I found was a person asking me about deep learning, which I had no idea at that time of what was that. And this means that these people in 2014, they already had some neural networks trained for recommender systems, and they were using those on in-house, no? So since then, Alexandros is best known for his work on deep learning for recommender systems, and today this is the topic he's going to talk about to us. So let's give a warm applause for him, and let's start the session.
Thanks a lot, John. I will take this into account in your evaluation this year. Okay, yeah, so as John mentioned, over the last 4 or 5 years, I've been working on this topic of deep learning for recommender systems. And I have to say, you know, I think this event is about Barcelona leading the way in some areas of deep learning, you know, and I think we can really say that in the area of recommender systems, you know, we were pioneers here in Barcelona in the Telefónica Research Lab, and we had some of the first actually papers of applying deep learnings for recommender systems, right? And then I'm gonna talk about them in the third part of my talk. So let's start. I think I don't need to explain to you what a recommender system is. By now, everybody interacts with them daily. You know, even when you're listening to music, when you're buying stuff on Amazon, you know, when you're watching movies, YouTube, you name it, there's a recommender system behind it. Even the advertisements you're seeing on some websites, they are probably recommended to you in one way or another, right? And actually, Oriol this morning gave us a small and nice introduction on how, you know, what's the basic technique of recommendation nowadays, and that is basically, or it was at least until recently, and that is basically matrix factorization, right? Where, you know, you have users on the rows of your matrix and the items that you want to recommend on the columns, and then you fill in some of the spots in this matrix with the feedback you get from the user. The feedback can be either clicks, views, you know, any kind of interaction you have. Traditionally, let's say this has been typically in many papers you will see that this is ratings, right? Mainly because of the Netflix data set, which actually contains ratings, right? This very old data from 2006. And then you take this this matrix and you try to decompose it in some way, you know, and you learn this kind of factors for each user and for each item. And using these factors, you can actually do recommendations by computing the inner product between a certain user factor, right? Let's say the third user there, and all the item factors, right? The higher the score that comes out, the more these two, the user and the item, match, and you can thus create recommendations, right? And that's, you know, that's the way recommendations have been done over the last, I don't know, maybe 10 or 15 years, more or less, you know. That's the go-to method for most recommendation methods, right? And of course, this is a rather suboptimal method in many ways, and we will see why later, right? And so, you know, when actually, as John was saying, when he came to interview with us in 2014, we already were thinking about how to move into deep learning because we were seeing that there's a lot of potential there in applying this method in recommendation, right? And there's another small catch here, which I'm going to reveal you later on, right? Who thinks this is a neural network? We'll see. Okay. So what does deep learning bring to recommender systems? Well, kind of the obvious things, and again, I think Oriol touched upon them in his talk, right? We have really, really good feature extractors now, right? I mean, these networks are really amazing in extracting. Also in the previous talk you saw, I mean, they extract really semantic information about, you know, what is in the audio, what is in the image. They can combine this, and it's really amazing, right? And they're super powerful in that, right? So maybe we can use them in doing recommendation, right? So the other thing is you can actually model the, let's say, sequential or dynamic behavior of a user, right? If you noticed in the previous sort of slide with this matrix factorization method, there's nothing there that includes, let's say, the temporal or sequential behavior of the user, right? The user might like some things at some point in time, but he might switch his preferences. And this is, of course, not easily, or actually it's very difficult to model that with the matrix factorization or standard collaborative filtering method, right? But we have deep learning methods that are really good in that, for example, recurrent neural networks, right? Or even convolutional neural networks. And of course, you know, deep learning is actually about learning representations, right? And recommendation is about learning representations for users and items. So there seems to be some kind of synergy there, right? Maybe we can use these techniques to learn good representations for our users and our items, and then use these representations to build good models, no? So these are kind of the fundamental ideas behind bringing deep learning into the recommendation system sort of community. And I have to say, we were pioneers in this area, as I mentioned, but somehow this community, the recommendation systems community, if it exists in some sense, and it does, you know, there's a dedicated conference and et cetera, it was is sort of resistant to change, no? They actually resisted in bringing in matrix factorization back in 2006 into the literature. They found that really kind of excessive, you know? They thought, yeah, it's too much, you know, too much math somehow. So, yeah. And so, you know, yeah, small story here. So we actually submitted the first paper on deep learning to this conference, the Recommender System Conference. Well, yeah. And it got ceremonially rejected with 3 strong rejects. So we thought, yeah, that's kind of a signal, right? So we took the same paper, worked a little bit more on it, and we submitted it to iClear, and it got accepted, right? So kind of tells you something, no? So, but yeah, I mean, back then I think there was 0 papers on deep learning and recommender systems, and now if you go to the same conference 4 years later, there's only deep learning and recommender systems papers, right? So there's been a complete flip, right? It's quite extraordinary, actually. So yeah, what are the kind of areas of research on deep learning right now and recommendations, right? I mean, one is obviously learning, as I mentioned, item and user embeddings, right? And we will see some really simple, actually, methods from NLP, et cetera, used with really big success in this area, right? Then the other is sort of extending this traditional collaborative filtering methods we had, right? And using these super advanced methods that we have right now in deep learning and sort of incorporating these methods into this, let's say, traditional methods. We call that deep collaborative filtering, right? Feature extraction, right? Wherever you have audio, image, video, right? You can extract really good features from this content. Use that for the recommendation system, no? And as I mentioned, session-based recommendations, which take into account sort of the dynamics of the session of the user, right? To try to model the sequential behavior of the user, no? Actually, that's where we did quite a lot of work at the group, yeah? And of course, you can combine all these things, right? I mean, that's kind of obvious, right? So let's have a look at the first sort of topic, right? Item embeddings and what we call 2-vec models, right? I mean, there's a whole zoo now of 2-vec models, right? Doc2vec, word2vec, pix2vec, whatever, no? And so, you know, obviously, these kind of methods have also creeped into the recommendation system literature, and I don't need to explain to you what embeddings are, but here's actually what I promised you before, right? You see this kind of model upstairs, that's sort of matrix factorization, right? You have the rating matrix, and you decompose that into the user factors and the item factors, and surprise, surprise, you can actually write it down as a simple 2-layer neural network, right? Where at the input you have the one-hot encoding of the user, and at the output you have the rating, the predicted ratings for the movies of this user, right? These 2 models are exactly equivalent. They can use exactly the same stochastic gradient descent method to optimize them, right? And actually, yeah, the whole community was using deep learning without knowing, basically. So it's okay, you know. And you know, then we have, you know, Mikolov in 2003 bringing in word2vec. And again, I'm gonna skip the things, right? I'm sure you all know that. You know, skipgram and SIBO, etc., right? And how you learn the embeddings for the words. No? And then you get this really powerful representations of words that you can then use in your NLP algorithms or whatever. And they have this really nice properties, right? King minus man plus woman equals queen. Really cool, right? And there's also sort of additional extensions of these models. For example, the doc2vec or paragraph2vec model published by Kwok in 2014. Basically, you replicate the same thing, and just for each document, you learn an additional vector, right? Which essentially encodes the context of this document, right? What is different of the difference of these documents to the other documents that are in your corpus, right? So you can use that as a representation of your document, right? Et cetera, right? Now, how can you use it in recommendations? Well, turns out like that a user, you can consider a user like a document, right? And you can consider the words in the document the items that the user has seen or consumed or watched or listened to, right? So for example, right, think of you have a Netflix account and you're watching over the year 30 movies, let's say, right? Then these 30 movies are the words in your document, right? And we can use these 30 movies and apply exactly the same technique as word2vec to learn representations for these items, right? For these movies. So basically, I don't have here a cursor. Yeah, it's okay. So you train this, let's say, item2vec model by one-hot encoding the item representations and trying to predict, removing one of the movies the user has seen and trying to predict this movie at the output of this network, right? And repeating that procedure of all users and all items that you have in your data, obviously. Right? In this way, you learn really, really good representations for these items, which you can then use to do, for example, item-to-item recommendation, right? The user clicks on an item, and then you just compute cosine similarities with all the embedded vectors of these items, and voila, you have a really nice recommendation system, right? That's super simple. Yeah, so basically that's the skipgram version of that, right? You just flip the whole thing around, and you given one item that the user has seen, you try to predict all the others, right? And that does exactly the same. And there are also different other versions of that. This is actually doing more or less the same thing, but instead of using items, it uses baskets of items, right? So you have baskets of items in the input, and you try to learn all the other baskets of items that the user has seen. And this is actually an equivalent model to the doc2vec, where instead of learning a representation for the document, you learn an additional representation for the user, right? You not only learn representations for the items, but also for the user that has interacted with these items, right? So these are all simple methods, but really, really powerful and really in use right now in the area of recommendation systems. Another, as I mentioned, another sort of topic in the area of recommender systems and deep learning is what we call deep collaborative filtering, right? And here, the go-to method is actually autoencoders, right? And the way, I'm gonna go straight to how they are used in recommendation. And the way you use these autoencoders in recommendation is you use the so-called denoising autoencoders, right? The really old version, right? And what you do is you sort of train in a corrupted data set. So you take the movies that the user has seen, you remove one movie, and you try to reconstruct the whole set of movies that the user has seen at the output of the autoencoder, right? So you use the autoencoder in a proper denoising setting, essentially, right? And in this way, the autoencoder learns the distribution of items that go together, more or less, you can imagine, right? So when you feed in the autoencoder the items that the user has seen, the autoencoder is going to try to complement them, right? And so it's going to recommend to you other items that are relevant to what you already have seen. And this is, again, super used in practice. It's been actually a really simple method as well. And there's been extensions that this was published in Wisdom 2016, but basically it's exactly the same model, just you add an additional node there for each user to sort of to personalize the autoencoder, right? It's just a tiny tweak, essentially. And of course, nowadays I think you cannot really give a proper deep learning talk without mentioning GANs, and you know, and of course the area of recommendations couldn't escape that. And we had a really nice paper actually this year, last year in SIGAR actually, the IRGAN, information retrieval GAN. And this is a nice work, and it uses sort of, this is quite specific to information retrieval, but it uses basically generative and discriminative models in information retrieval. Think of generative models as models that given a user, a complete ranking of items that are relevant for this user. While discriminative models are the models that for each individual item model the joint probability of this item and the user, right? So each individual item, they will give you a score of if this item is relevant to the user or not. Now you have these two classes of models where you can use the same family of models, in fact, neural networks, surprise, surprise. But they are sort of slightly different, and you can let them play this adversarial game, right? You can let the generator generate a ranking of items, and this discriminator evaluate that if this item is actually relevant to the user or not, right? Is it in the data set or not? That's exactly the question and the game that is played, right? And in this way, you generate really, really good generators and really, really good discriminators as well. And this method works amazingly well. Right. And another way to look at the recommendation problem, I don't know if you're familiar sort of with graphs, and, is a link prediction problem, right? So we mentioned, right, we've seen sort of the representation of the data in this matrix where you have users and items, right, and ratings. But you can actually represent this matrix as a bipartite graph, right, where you have one class of nodes, which are your users, and another class of nodes, which are your items. And interaction between a user and an item is represented by an edge, right, between the user and the item. Okay, users, you have them here in pink, and items in blue. Okay, and then the task is actually to predict new probable links, right, between users and items, right? And one class of methods that has been actually proposed recently for this task is graph convolutional networks, right? And graph convolutional networks actually work by propagating the features of each node to the neighboring nodes, right? Multiplying with a model matrix which is learned, et cetera, but that's the main ideas. So basically the features of neighboring nodes end up being very, very similar, right? And you can repeat this process several times, and this corresponds to having several layers of this graph convolutional networks, right? And in this way, you learn really good representations both for the users and the items. And you can then use these representations to do prediction in the same way you would do it more or less in a matrix factorization setting, where you essentially compute the similarity between users and items, right? But here, the factors of the users and items, the latent factors, right? And this, again, is actually an area which is really interesting, and there's been quite a bit of research in that. The third sort of class of methods that I wanted to talk about is this feature extraction from content, right? And here, obviously, let me skip that. You can actually easily see where that could be useful. For example, you're shopping stuff on Amazon. You're probably going to look at the picture of the item that you're buying before you read the description. So the picture is actually carrying a lot of information, right? And if you could extract that information and include it in your recommendation problem, that would be obviously quite useful, no? And so I think, yeah, 2016 paper, ICML paper actually by Macaulay, where they actually use a pre-trained CNN, nothing special, I think a GoogleNet or something like that. They extract features from the image, and they take these features and concatenate them to the item feature that they get from a matrix factorization, right? And then basically do another matrix factorization for that, and use these embeddings, the joint embeddings of the image and the item, to do recommendations, right? And this leads to quite significant gains in the Amazon data set. I think they used between 10 and 25%, right? And I won't mention too much about that, or you all talked actually about what Pandora is doing. It's exactly this, right? They're using features from audio to enhance their matrix factorization, right? For the problem of the cold start, which is super, super strong in the area of music recommendation, right? Everybody listens basically to the same song the whole time. So nothing else gets data. And again, there's similar sort of methods used for text, where obviously recurrent neural network and convolutional neural network are used to extract information from the text. And this type of models have been used for paper recommendation, news recommendation, et cetera, right? Where obviously the text content is super relevant. No? And finally, the session-based recommendations with recurrent neural networks. As I mentioned, when you shop, you're probably not going to stop at one item. You're going to click around, right? It's kind of the equivalent of walking around the shop to see what there is, right? So let's say you want to buy a coffee machine, and you click over 6 or 7 items, and in the end, you decide to buy one, right? So what this will do over a period of 10 or 15 minutes is that you're going to generate a stream of clicks, right? You're going to generate 6, 8, 10 clicks in your session, no? And of course, you're not the only one shopping. So we have several users that are shopping, no? And if you're not Amazon, let's say, and you're not logged in, and you're in a small e-commerce store, right? The logs that you're generating are basically anonymous, right? The only thing we have is a session ID that describes your session, right? And the clicks that you've done, right? So how do we generate recommendations here? That's quite a tricky problem, right? Because we don't know your past history. So, well, we have really a good, powerful method to model these sequences, recurrent neural networks. And basically, we have a sequence of events, and we want to sort of try to recommend you or predict what the good next click for you would be. So we can actually use the recurrent neural networks to do that. And that's actually an area where the traditional recommendation algorithms are failing completely, right? And actually, this whole, let's say, treatment of the session as a sequential problem didn't exist 3 years ago, right? But now you have about 300 papers on the topic, mainly using recurrent neural networks, right? So yeah, what we did is basically we took a recurrent neural network and we sort of adapted it a little bit, right? We changed quite a few things. We got rid of the categorical cross entropy loss. We use a ranking loss function. We created a special mini-batch system that actually, because the sessions are really, really short, right? You cannot really create big mini-batches with a single session. So what we did is we actually stacked one session on top of the other and create parallel mini-batches, right? And yeah, we used actually GRUs because actually we didn't see any big differences between GRUs and LSTMs. So, and these were actually much less, they used much less memory. And we had very small GPUs back then. So yeah, and this was published in 2016 at iClear. Here, basically some of the technical details, not so important. What we played around a bit, but basically the main result is that we got 30% improvement compared to the best baseline at the time, right? This actually we worked a little bit more on that recently, and we improved that another 30%, right? So we currently have a method that is 60% better than the baselines in session-based recommendation, and it's actually deployed in many recommender systems across the world. In fact, if anybody of you uses Apple Music, they're actually using not only our method, they're using our code. So that's quite, yeah. I mean, they could have paid a bit, right? Yeah, I mean, come on, it's Apple. Yeah. Yeah, an engineer came to me at the conference and told me this, right? I'm not making this up. Yeah, so, you have, as I mentioned, you have this sort of simple recommendation setting where you have sort of the sessions, right? And you can see, let's say, one user is watching soccer, and then the other user is watching cartoons, and then the other user is, let's say they're watching videos, right, on YouTube. But again, you might have a sort of slightly different setting, right? And this happens with big recommender systems. YouTube, for example, almost certainly any YouTube video you're watching is recorded on your Google account. because you probably all of you are logged in your browser and your Google accounts, and so when you're watching YouTube videos, Google knows all your sessions, right? You watch these 3 videos, and then you watch these other 2 videos, etc., 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 right? So you're actually in this setting where Google knows what user is creating each session, right? And it knows that the first session and the third session actually came from the same user, right? Who's watching the sport videos, okay? So now this is an interesting information, right? Because until now, our RNN could only treat sort of single sessions. How can we deal with multiple sessions? Well, one sort of easy thing is just concatenate them, right? Just assume that it's a huge stream of data coming from the same user and forget about the user being not watching videos for 3 days, doesn't matter, right? Just one big stream and just model that with the recurrent neural network. Works better than just not doing that, right? Just works better than just treating each session as an individual session. It's okay, but you can do something better. Right, you can use what is called a hierarchical RNN, right? And what is a hierarchical RNN? Basically, a hierarchical RNN is 2 RNNs. One RNN does exactly what we discussed, right? It's just trying to predict the next video that the user is going to watch, right? The other RNN waits until the end of the session, right? And then takes as an input the last hidden state of the first RNN. Right? And then tries to predict a good initialization for the hidden state of this RNN that does the sequence prediction for the next session. Right? So you can think of it as the second RNN tries to guess what the state of the user is going to be the next time he's going to watch a video, right? And this is actually working amazingly well. It works way, way better than just concatenating the states. Here we have the whole sort of model. We tried a couple of variations of this. They're not really that important, but what is important is that that's basically what the second RNN does is taking in as an input the hidden state and then trying to predict a good second hidden state. Yeah, and so that work was published I think last year. Yeah, at RecSys with Massimo, who's actually now at Pandora. He's working with Oriol together. Huh? And our sort of recent work is actually also was mentioned. The models that we're using were also mentioned in one of the previous talk. They're actually this kind of diluted convolutional networks that were inspired by WaveNet, and all these and ByteNet models, etc., etc. And it turns out this diluted convolutional networks are really, really good in capturing sort of long dependencies in the sequences. And we use them to do the sequence prediction task for the session-based recommendation task, and they also work really, really well. It turns out they're also quite a bit faster than sort of recurrent neural networks because they're essentially filters, right? Whereby in recurrent neural networks you have lots of matrix vector operations that you need to do for every time you do an inference step, right? So. Yeah, as I mentioned, it seems that deep learning has now entered pretty strongly in the area of recommendation systems, not only audio and vision, right? So, and it's really an interesting area, right, to work in. The data is really diverse. There's a lot of data. There's a huge commercial interest. There's sort of a mismatch between the sort of application of these models and systems and the time it takes for modern machine learning methods to enter in that domain, right? It's quite of an interesting thing. And obviously there's a huge potential, right? I mean, the first paper about GANs and recommender system was published just last year, and I think there's maybe one more or something like that. And obviously, this is an area where, for example, deep reinforcement learning methods can be super, super interesting. And again, there's been little work in the area, and I think there's sort of an open research field there to do things, and there's a lot of data as well available, right? Any questions?